Thank you very much for that wonderful introduction. Of course, you don't go on your phone now because that would be evil to figure out what I publish. You will do that later. I'm going to talk to you about the relationship between AI and chemistry. And it's a circle, as you will see. So it's like AI for chemistry, for AI, it's sort of with periodic boundary conditions. And we'll go through that circle as in this talk. So the main actor of today is the free energy, and I'll talk to you a little bit about, everybody should know the free energy in this room, what that is, but I'll connect the free energy in chemistry to the free energy in machine learning, and I'll argue that's exactly the same thing, in fact. And then I'll talk about what chemistry and physics have done for AI so far, and you'll be surprised that, in fact, the most powerful algorithms that we use in AI are based in chemistry. This is interesting. And then I'll go and show how, in return, AI can influence chemistry and is currently already influencing chemistry. And maybe that's the most important part for you. I'll go through a few projects very briefly that I'm involved in, and then I'll finally conclude. So here then for the introduction. So that's the equation for the free energy. It has three terms. Free energy equals energy minus entropy. And it's related to the industrial revolutions that we are going through. The first one is the Industrial Revolution, where human labor got replaced by machine labor. So that's kind of the energy term in the free energy. And now we're in the information revolution, or the digital revolution, where information that people do, so reasoning and thinking is going to be replaced by AI, right? And so that's the entropy part in the equation. And if that was too abstract, so here is sort of this same thing expressed in two Dutch heroes. The first one is Daphne Schippers, world champion in the 200 meters race. That stands for raw work and power. And then Ben Feringa, our Nobel Prize winner in 2016, stands for information and knowledge, and that would be then the entropy part. So I believe that deep inside, basically these things are very related, and this is what I will argue today. So there's this beautiful quote from John Archibald Wheeler that says, so it from bit, which is his way of sort of saying this, it from bit symbolizes the idea that every item of the physical world has at bottom an immaterial source and explanation, that all things physical are information theoretic in origin. I feel that's a very, very deep statement. I won't go very far, but you can read about black holes and all that kind of stuff, and that's where these people think about that. I'll just try to sort of argue this at a sort of more chemistry level. And this is, I find a beautiful paper by James, and so this is called Information Theory and Statistical Mechanics, that he basically argues that these things are very deeply related. And the most important part here is that entropy is our degree of ignorance about the microscopic degrees of freedom of a system. And that's actually a very deep statement, because many people think entropy is a property of the physical system itself, and he argues it's not. And there's many, it's not just James, who's more like a statistician, there's also chemists and physicists who argue this. It's our degree of ignorance about the system, so it's an epistemic quantity and not an ontological quantity. And why do I think this is important? Because in machine learning, this is exactly how we think about probabilities. When we write down a probability, it represents our uncertainty about all the degrees of freedom that we don't know about the world. The world is in one state, it's one thing, but we can't observe everything. And that's when we write down entropies and write down probabilities. And my argument, and with many with me, say that this is exactly the same in chemistry as well. And I'm going to throw an equation at you. I hope that's okay. This is the only two equations you'll get to see, by the way, so that's okay, I think. And the reason I'm doing this is I want to contrast the two core equations that we use in machine learning and chemistry. So on the left-hand side, That equation is the equation what we call the evidence lower bound in machine learning. And let me explain it. So there says minus log p of x. P of x is the probability that the data set X has under our model. So P is our model, and we want a good model assigns high probability to data X. And it says that minus log P is smaller or equal than the expected value under a other distribution Q, it's called the variational distribution, Q of Z, given X, where Z is the microscopic degrees of freedom of the system, the things that we don't know about the world, where X are our observations. Of the minus log P of X gives Z, that's our model, and then minus the entropy of Q. And that's the core equation that we use in machine learning. Now on this side, this is, I feel, the core equation of chemistry. It says that the free energy of a system at equilibrium is smaller or equal than the variational free energy, which is on the right, which is the expected energy, the expectation of the Hamiltonian under the distribution Q, which is not at equilibrium at this point, minus T temperature times the entropy. So that's the variational free energy. And this thing comes down as the system relaxes towards equilibrium, and the equilibrium distribution is the Boltzmann distribution. Now the point I want to make is that these two equations are identical. They are the same. And no, there's an X there. That's because I've explicitly written the observations. Where here you could also write observations, and maybe the core, that's maybe temperature and number of particles, or the things that you keep constant in your system. But Z are the microscopic degrees of freedom. They're the same here. Here we think of Q as all the things we don't know, and I've just argued here one should also think of Q as all the distribution that results from the fact that we don't know everything. Okay, so I find this actually quite deep. And to maybe push this a little harder, we have an algorithm in machine learning, a very core algorithm called expectation maximization. And there's two steps in that algorithm. There's the E step, and in the E step you update Q to minimize that bound. So it's like you relax the system to equilibrium, keeping P fixed. There's the M step, where you keep Q fixed and you update P. And that's the learning step, where you change your model. Okay, what does that mean in thermodynamics? When you update Q, you relax the system, you basically compute your entropy production in the system, or the amount of heat that you actually either absorb or radiate out. That's at fixed Hamiltonian. Now, if you update P given Q, that's exactly like performing work, right? And so the free energy, right, the heat and the work is again in there, and this optimization algorithm exactly mirrors work and entropy in the real world. Okay, so in 2015, this paper was written. And I'm going to argue that this is an absolutely key paper that has transformed AI as we know it. And it says deep unsupervised learning using non-equilibrium thermodynamics. Okay, so you can see that's clearly, chemistry, right? So, but this was a machine learning paper. And if you read it, you actually read about the Jarzynski inequality in that paper. So they talk about the Jarzynski inequality in that paper. In our field, this is called annealed importance sampling. And what that paper does, it proposes a way to basically say, okay, take some distribution that you're interested in, the data distribution, and sort of add noise until you diffuse it all the way to a Gaussian blob. And then you learn to undo that. So you learn to go in the opposite direction, where you take a point here and you map it back onto the manifold. And you do that by computing vector fields, so that you know that every point sort of moves along the gradient of a vector field back onto the manifold. So that was 2015. It didn't work so well, because with many of these things, you need to be able to train them efficiently. So what in 2021, there was a breakthrough again by these people. And they took exactly the same idea, but they made it train very quickly. And they mapped it onto basically Brownian motion. So you start with an image, and you slowly add noise to it. So this is the second law of thermodynamics in action, right? And it's Brownian motion. There's a drift term and there's a noise term. Actually, I said this was the last equation. This is really the last equation, I think. Sorry about that. All right. And so what they do is then they learn the system to do the inverse of that. So, and you can show that the inverse of Brownian motion is actually this equation. So you pick up this extra term. So this is the inverse kernel that gets you from a noisy image back to the original image. And this is called the score function. And you train a neural network to replace this. And you have many sort of examples because you know all these pairs. And you can just train it to go back from this thing back to that thing. And they made that work. They make that work very efficiently. Okay, so that's just thermodynamics, right, with a bit of machine learning on it. Now, if you do this, right, and you run this, what will happen, right? And you do this on images. Okay, I'll just give you a few examples of what will happen if this thing goes forward. Yeah. So this is what you can do with that, right? So this is thermodynamics applied to images. So you can just stick in a random number, maybe a text prompt, and it will generate the most beautiful images for you, right? That's amazing, right? So all of this AI stuff is coming actually out of chemistry in some sense. You can even win competitions. So this is a fake photograph that won a competition generated by AI, and this is a fake painting that was generated by AI, also won a competition, and the artists weren't happy, of course. And you can generate videos with it, right? So here's a bunch of videos. This is a dog licking an ice cream. You can do all sorts of funny stuff with that, but of course this still looks a little awkward, but give it a few more years and you can generate entire movies with this, I'm sure. Now I'm going to cycle back to the opposite direction. So we've now used thermodynamics to generate the best AI algorithms that are there, and now I'm going to use those AI algorithms again to help us solve chemistry problems. And so this is with this team here of very talented individuals. We implemented an algorithm. Well, they implemented an algorithm, obviously. I didn't do that at all. But where you start with your noisy blob. So this is the cat, and this is the noisy blob. And you start with a noisy blob, and you turn that into a viable molecule by this denoising process, right? There's a bit more fun stuff that goes into that, which has to do with the symmetries of the world, so you can make this whole thing understand that a rotated molecule is actually the same molecule, not something else. So we put that into there. And then here's a little movie of how that works. So this is basically generating an image as you go through time, but then it's an actual molecule. And we check that these molecules are actually thermodynamically stable molecules. You can in principle make them. And the name of the game is, of course, now to say, I want a molecule with these properties generated for me, and then it will generate that for you. That's a little harder, but I think we're making a lot of progress in that domain. Okay, so now then more on the opposite side, right? So we are going to try to see if we can apply this AI to the sciences. And so here's all of the sciences, and it's amazing that it spans enormous spatial temporal scales all the way from picometers to light years, etc. But chemistry obviously is sitting here at this little corner right on the edge between quantum and classical physics, right? And so, yep, there we are. That's what we're going to focus on. And so one of the, maybe the most important contributions of AI towards chemistry and physics and biology is this AlphaFold by DeepMind, where you give it the sequence of amino acids, and it will fold for you, it will determine for you the three-dimensional structure of the resulting protein. And of course, the three-dimensional structure is important for the functionality of that protein, and so this is an incredibly important contribution. They might even win the Nobel Prize one day for this, I predict, because they have basically created the three-dimensional structures for almost all of the proteins that are in the human body. And it's not the last word, but certainly very useful for biologists, right? And so what has been happening recently in this field, also in big companies like Microsoft and also Google, in big companies, they have access to a lot of compute. They have started to leverage that compute so that instead of doing experiments in the physical world, they're now doing experiments in silico, in computers, right? So in the old days when people tried to make new chemical compounds, they just did a lot of trial and error. Later, you design things, you collect a lot of data, you do experiments, collect a lot of data, and from that data you try to improve things. So these days, much of that of that experiment can be done in a computer itself, right? And so you do in silico computation. So that's certainly a trend, but that's not the paradigm shift. So it says here, entering the fifth paradigm for chemistry, I think that fifth paradigm term was invented actually at Microsoft by my former boss, Chris Bishop, and his boss, I think, Peter Lee. They wrote a blog about that. It's the fifth paradigm. Now, what is that fifth paradigm? Yeah. So I invite you to sort of go through this little sort of example. So if you like cars, so you design a car and you put it in a wind tunnel. So the latest version of the wind tunnel is all digital, so you can just run it in your computer, right? And then if you have a new car, you could go to this digital wind tunnel again and do the experiment again. But that's actually very expensive because these real or digital wind tunnels cost a lot of compute or time and money. But now the fifth paradigm is to not do that every time again. To basically do many of these, then collect the data on these experiments, and then train a neural network. And then the neural network can accelerate this particular wind tunnel experiment. It can even maybe predict the full outcome, or you can just use it to accelerate this experiment. And this has been done already quite successfully for weather prediction, where the latest weather prediction models are as good or better than the numerical simulators, but 10,000 times more efficient. So 10,000 times, that's 4 orders of magnitude, it's not bad. Okay, so how does that particular paradigm shift, how is that important for chemistry? So here's a couple of examples of where it can be applied. So this is the time-dependent Schrödinger equation. This is a beautiful visualization by Quantum Magazine of these blobs, which are then the actual sort of electron cloud. And you can try to sort of avoid the actual quantum mechanical calculation, but use machine learning to accelerate that. Basically, in DFT, you can then replace or learn the free energy functional and then use DFT calculations on it. And then here is molecular dynamics. So this is the Langevin equation. It's also a stochastic gradient descent, stochastic differential equation. And here, it's also very expensive because you need to compute the forces on the molecules, and those are replaced now by a force field. So that's actually already a very effective way to accelerate MD simulations. Also many orders of magnitude, and this is this weather which I just mentioned, is the Navier-Stokes equation, and we can now predict the weather patterns with neural networks way more efficient at no loss of accuracy. And there's beautiful applications in drug discovery, in catalysis, and in material science. How much more time do I have?
13 minutes.
13? Oh, excellent. Okay, so then now I'm going to just go a little deeper maybe in seeing where machine learning can help out by this diagram. So let's start in this corner. I just mentioned quantum DFT. We have an expert here, Paula, somewhere here in the audience, who knows all about this. In the back there, she'll be in the panel, I think. So quantum DFT can be accelerated by learning something about the free energy, the free energy functional, and using that inside the quantum DFT calculations. So the top line is continuous methods, and then the bottom line is discrete methods. And as we go through this, we go up in scale. So when we go to MCMC methods, MCMC methods can be accelerated with machine learning tools. Then we go to Boltzmann generators, where you don't actually sequentially generate samples, but you'll generate them at once from the equilibrium distribution. Beautiful work by Frank Noe and collaborators. And then here in this corner is classical DFT. It's at the thermodynamic level, but it's sort of the same technology as here, minus the sort of quantum effects, but it's the same tools. And so you see there's actually an interesting bridge here from across the scales, but using the same methods to describe the physics. So this is equilibrium methods, and then there is a sort of similar thing for non-equilibrium methods, where you would have the Schrödinger, the time-dependent Schrödinger equation, which with neural methods you can also model. Molecular dynamics, you can accelerate that with force fields, etc. Dissipative particle dynamics, or conditional sampling, where you sample a future state of an MD simulator given a current state using a neural net. And then here's hydrodynamics, the Navier-Stokes equations and such. And then again, there is a beautiful bridge here. So this is continuum and this is discrete. And there's also a nice bridge because you can actually view the Schrödinger equation as sort of a hydrodynamics equation. Okay, and in all of these, I believe you can effectively inject machine learning tools. And then I'll just go over a few of these things in a little bit more detail. These are some projects I'm involved in, but there's many, many more projects around. So this is a project with these two smart students at EPFL and in Bruno Carreira's lab. And here we basically say, okay, so we have a pocket, we have a protein, and we know the protein, so we know the pocket. And what we want is we want to generate a drug-like molecule which sticks inside of that pocket so that it can sort of neutralize, that particular protein, right? And it's again this trick of this diffusion-based models. And so here you see, how that works. So there's the pocket, and the model it sort of generates sort of the molecule in this thing using this sort of denoising method that I described for images as well. You can even put fragments in. You can say, okay, I want these fragments to stick into these part of the pocket and then sort of finish the molecule off yourself, right? And then, it does a pretty good job. Although this is something that's still in development and, going very fast, improving very fast. So if you think, well, that doesn't look like a drug-like molecule at all, it doesn't work, right? Wait a couple of months and then it will start working a lot better. These things are on a very steep curve. Here's another project. So this is something that's probably quite dear to some of the chemists here in Amsterdam. Transition path sampling. It's collaboration with Bernd. And in transition path sampling, I call this actually the Sisyphus project. And the reason is that, so Sisyphus was this poor guy which had to roll up this rock on a mountain. And then when he was right there, it will all come back, right? And we'd have to do this forever. So I think this is somewhat like how a chemists would feel when he's doing an MD simulation and trying to get a molecule over an energy barrier. It also takes about forever, and you need a number of fluctuations all aligned in the perfect way to get over that energy barrier, and of course it never happens. And so what we decided is to help Sisyphus a little bit, and we were going to add a force. So on every atom, we are going to add a force that will slowly move this molecule from one conformation to the other conformation. And basically, it has another equation. Oh, I'm sorry. So, okay, anyway, here's another equation. So this is a Langevin dynamics. So the change in the location is given by the velocity, and this change in the velocity is given by the force plus an actual external force, a controlled force that you'll add to this thing. So now we've mapped this problem onto a optimal control problem or a reinforcement learning problem, and we can learn what that force should be in order to get it over this energy barrier, performing the least amount of work. And so this is with this smart group of people, and this is already somewhat older visualizations. The system already works quite a bit better now, but you can just see here the molecule as we force it over the free energy surface with this external force, and there it goes, and it needs to get to that sort of minimum there. And you can sort of track it. If you know these molecules, then you know that that's a nice path to take for it. Okay, and then you can go to larger molecules, but maybe I'll just skip that. You can just watch them fold and move from one conformation to the other conformation. I believe this is a very exciting direction, and we're still working on that. And here's the final project I want to briefly mention. This is with a PhD student Jacobus Dijkman, and also with Bernd and Jan Willem van der Meent. And this is this classical DFT which I mentioned. And in classical DFT, so you have this free energy, and you're trying to sort of learn a free energy such that if you go down on that free energy, you get to the right density profile for your system. And I mean, this is not very clear. It doesn't matter, but it's like these are the first results that show that you can indeed train this system to reproduce basically the physics and to produce the densities that you would expect for the real system under any sort of external potential. Okay, I'm going to slowly end. So why I'm very excited about this field, I think we might slowly move to what I would call a golden age of materials. And I find it intriguing that we have named the ages in which humanity lived to the tools that they used, or actually the materials that they used. So we went from Stone Age to Bronze Age to Iron Age. We're probably in the Plastic Age right now, or worse, some other bad things in our environment. But my hope is that at some point we can go to the material on demand age. So basically that we can build search engines where you would say, I need a material with these particular properties, and it will spit out like 100 candidates of materials which have approximately those properties. And the reason I think, there is sort of a perfect storm is that, there is these fields in molecular science which have matured to a high degree, and then add to that the computational fields, which are all in full develop now, computational science on supercomputers, machine learning, of course, with AI right now, and then in the future, quantum computing, right? Because the first thing a quantum computer is supposedly going to do well is to do quantum mechanical simulations, right? So that will be the first thing that hopefully they get good at. And then maybe most importantly, there's these applications which will only increase in importance, right? I mean, healthcare with pandemics or, new antibiotics that can tackle sort of resistant strains of bacteria. The energy transition, where we want to find better ways to split water into hydrogen and oxygen, or better fertilizers. And in sustainability, maybe new materials, new materials to capture carbon out of the air, or new biodegradable plastics, or these kinds of things. All of these things are, can certainly be accelerated with AI. And then to conclude, so I honestly believe there's a very deep connection between AI and chemistry. I would argue that the best algorithms in AI are inspired by chemistry. And now we can pay back. I think AI will also be a super powerful tool, a new tool for chemistry. And I hope, of course, that we can use that tool for the better in terms of health and sustainability for new drugs and materials. Thank you.
So you're Thor, and I guess this makes you Odin, and we have 2 minutes of questions for Odin. Yes.
This is a mic?
Yes.
Okay. Thank you for the very nice talk. You gave some examples of using diffusion models for molecule generation. Yep. These diffusion models are trained based on the chemistry that we know of, right?
Yes.
Are there ways to let the machine learning models explore the perimeter space that are, beyond our human knowledge at the moment?
Yeah, I believe so. So these models, they're trained on. I mean, this is the problem of generalization in some sense in machine learning, which is that if you train on any very, very peculiar set of molecules, you might only expect it to do well in that particular space. But if it starts to capture something about the actual physics, about what does make molecules stable things, or what kind of properties do they have, and you manage to learn it such that it generalizes these particular concepts also to new domains, there is hope that it will generalize. But I would also say that is the key issue in some sense, right? So because you might put a lot of time in training for one problem, and you need a lot of data to generate in that particular domain. And then, of course, if you can only do things in that domain, it's not super useful because you already have done lots of simulations. So it's really key to see if you can generalize this to other domains. But I do believe there's a good chance that it can learn the actual laws of physics. Yeah, I mean, in weather prediction, it's somewhat similar, and it seems to do pretty well. Yeah.
We take one 45-second question and answer. So, Odin, ready? Thor, better have it sharp.
It's a very short question anyhow. Have you already been working on learning these core concepts, like learning it physics, like adding the real physical properties of these molecules to try and expand it? Is there already work being done on that?
Oh yeah, so there is definitely ways to do that, right? So in all of these, that's sort of the game in some sense. Symmetries are one of them, but there's And you should probably talk to Paula at some point. But you know, the whole idea is to see if there's all sorts of boundary conditions, for instance, for quantum DFT, you can sort of add into the system, and so that it will understand all these limits and extreme cases, or maybe you know something about the actual potential for the problem. You don't have to learn all of that. So putting in these inductive biases into these models, I think, is the core game that we need to play, and people are definitely doing that. But yeah.
So once again, thank you, Max.